what I wanted to do was to do dimensional analysis problems and some problems on drag.
Go for it. That's perfect.
That sounds good.
Yep, sounds perfect.
So I'm kind of going to work through these problems here, some of these problems.
Go for it.
And maybe some other things. Okay, so how many people have looked at these dimensional analysis problems? Any troubles with them? Well, you don't even know what the answers are, but I'm sure. Okay, well, let's just work. They're all pretty much the same, right? But there's some differences. The last one's kind of complicated. Let's see. Yeah, problem number 4 on this set is more of a similitude problem. So I'm not sure we have enough time to go through that one. That's pretty long, but I did problem 1 already. I did problem 1 in the morning session. So the answer, just for your reference, the answer to problem number 1 of the answers is, what is this problem? Right, torque. The answer is, one of the answers, torque over the force, and this was a problem. What is the problem here? The problem was you have a disk spinning around like that, and you have a force on this thing, right? And it's supposed to be used to polish a car, right? And the viscosity of the fluid is mu, and the roughness. What is the roughness of? The roughness of the fountain paste is E, and the rotation rate is omega. What else? Sigma is the surface tension. Sigma is the surface tension. And yes, and the torque is right. And the torque is the thing you're really after, right? Let's see, what are we after? So the problem would be, erase this. So the problem is the torque that is produced. So I guess the idea here is you're pressing down on this thing and this disk is spinning around. And the question is, how much torque is required to give you a certain omega, I guess. That's pretty much what the problem is, right? So it makes sense in this problem. Of course, you could phrase it many different ways, but that's the way we're phrasing it here. Obviously, you could do another problem. You could say, well, what is the omega, given an F, what is the omega to produce a torque, right? So there's several different ways you could attack it, right? And depending upon which way you think about it, then a different variable will become the dependent variable, right? But in this particular case, what we're saying is, we're given an F, and we're given an omega. So the question is, what is the torque in general? Yeah.
You said on the exam, you're going to give us the dependent variable.
Yeah. I'm going to give you the dependent variable, and then, of course, the other, right. So in this case, the assumption is that torque is the dependent variable. And so the torque has to be a function of everything else. And everything else is F, omega, U, E, sigma, and what else? Am I missing anything? 1, 2, 3, 4, 5, 6. I think that's it. Right. So these, I have no idea what surface tension has to do with the problem, but it's just includes the problem for some reason. It may not have anything to do with it, but it doesn't really hurt to put it in there. You may find that it might form a dimensional group, which is not important at all, but you're going to get something. So all these three guys are the fluid properties, and these are the forces and or kinematical quantities or dynamic quantities. And so we did this one in class, but let's briefly review it. We're not going to go through the whole thing. Let's briefly review this. So let's see. What is the first step in this problem? Well, this is, of course, the first step, right? This is the first step. That's step number 1. Step number 2. What is step number 2?
Setting the units.
Yes, get the units of every single variable, and I'm not going to do that for this problem because all the units are, we discussed those units before, right? Any particular unit here that you're confused about? Surface tension maybe? Well, on a test, surface tension will be given to you. But surface tension, this says the units of length, of course. Surface tension is force per unit length. And I mean, you could do these problems with force, length, and time if you want. Could. But for some reason, I like ML and T. It doesn't really matter, whichever one you like, FLT or MLT. Okay, so this is force over length. Viscosity will be given to you. I believe it's ML. What is it? I always get viscosity confused. What is viscosity? I think it's M over LT, right? M over LT. Omega is seconds to the time to the minus 1. Force is obvious. Torque is force times length, etc. Okay, so that's number 2. Number 3, what's step number 3?
Find the number of pi groups.
Correct. Number of pi groups. Correct. And in this case, what is the answer we have? 1, and I guess I told you guys several times, count them accurately. Sit there and make sure you count them correctly. Several students are always miscounting after a while. Count them 3 times. This is one of them you must include, all of them. 1, 2, 3, 4, 5, 6. Am I right there? 1, I'll do it again. 1, 2, 3, 4, 5, 6. If you make a mistake on that, then of course you're in trouble. Minus what? Right. In this case, it's 3 MLT. You could have, obviously, you could have a problem that's less than MLT. You could have a problem that's more than MLT, because we can certainly have use Kelvin in there too. So we have 3 fundamental units, and so we know we've got to have 3 pi groups. Okay, so we got that one, and what's the 4th step? Repeating variables, yes. Just follow the same steps over and over again. Same thing for all the problems. There are sometimes some weird things happen, but generally speaking not. So what are the rules for repeating variables? Well, they have to have, in this case, they have to have ML and T in them as a group set. Right? So in this case, ML and T. So they have to have ML and T in them. Now, suppose you only had M and L, then the repeating variables will only have to have M and L. In this case, they must contain among them ML and T. Also, you pretty much know how many there are from this. So you know you've got to have 3 pi groups, right? So that means if I pick arbitrarily this one, I have 3 left, so that works. Therefore, it's pretty clear I have to have 3 repeating variables, RV, repeating variables. I've got to have 3 of them. Then last requirement, did anybody remember the last requirement? They cannot form a dimensionless group, right? So I'll just say no pi group. I guess if you pick them and they do form a pi group, then you've already got your pi group already. So there's no point in it. Okay, so that's it. I guess I should say that after a while, you could certainly, once you've got all the dimensions here, the 2 big things are this number is really important, and of course getting all these units down, correct? once you've got all that, if you're really, really good at this, you can probably figure out the pi groups without going through anything else. You could. If it's not too, if there aren't too many variables. But the way we're just going to do it the brute force way, without guessing.
Dr. Handler?
Yeah.
So I had two questions. You said on the exam we provided the units for every
Yes.
omega.
I'll give you all the units.
Okay. And second question, so whenever we're getting the repeating variables, and then we have 3 repeating variables, so let's say if we had, instead of MLT, we had MLTK, and it would be 6 minus 4, would we have 2 repeating variables?
No, that's a good point. So suppose that we're ML, okay, so remember that. So you've got 1, 2, 3, 4 repeating variables, right?
Right.
But there's only 2 left over. So there's only going to be 2 pi groups.
Right.
Right? So the number of repeating variables would be 4, and you got four variables. 4. Okay, let's see. Well, the next step, of course, is actually getting it. And I'm just going to write down the answer. We'll do another problem in detail. So 1 pi group, we'll talk about this in a second. One answer to this problem is this one. That's an answer. Okay. And we got that by the standard technique, which we're going to go over. And let's see. So let's just check to make sure that at least one of these things is mentioned. Let's check this one. Let's see. Torque is, well, I'll just use force for now. Force times a length divided by a force. That's where I get that force. And this is a length, so there's no doubt about that one, etc. So these are definitely dimensionless groups. Now, can somebody write down another perfectly good solution to this? Tell me how you would get another solution to this problem without doing the problems. If I tell you that's a solution, give me it. How am I going to get another one? Do what? Yeah, pick different repeating variables if you can. But without even doing that, can you tell me? Can you give me another answer? Without even doing hardly any work at all. Remember, so this number, whatever it is non-dimensional. This one's non-dimensional. That one's non-dimensional. Yeah, right. You can do anything you want with these guys, right? So, for example, so let's just say pi 1 is a function of pi 2, or pi 3. I could get another solution. Let's say pi 1, for example, is a function of, let's just see. Okay, I'll just do something that's kind of silly. I'll just take pi 2 and divide it by pi 1 squared, comma, pi 3. That's a perfectly good answer. Yeah, it's a perfectly good answer. Right. It's you could probably get that answer if you picked a different pi group. I don't know. I picked a different repeat variable. Let's see. I can make this divided by pi 1 also. That would be another answer. I could raise this to the 75th power. That's still a perfectly valid answer. It doesn't matter, right? Oh, sorry. Yes, I could. I could take this pi group and multiply. I would never do that, but it doesn't make any sense to do that, but you can do it. I could take the square root of this one. That's perfectly okay.
So you don't have to do the same thing to both pi groups.
No, you don't. Because after all, these are all non-dimensional numbers. I mean, they're obviously kind of silly. Why I don't know why I do that, but it's perfectly okay. So the answer is that you might get one answer, you might get another answer. You could be both correct. Yeah.
Does pi 1 ever change? Do we ever do anything with pi 1?
Sure, you can do anything you want with pi 1. Let's see, I can take, well, yes, sure, I can take pi 1 divided by pi 3. That's okay too. I can even multiply this by the 350th power. That's perfectly good. Still be valid. Don't do that in a test.
So for example, if you said provide 3 different solutions for this problem, we could just solve it 3 one time and then just
Solve it one time and do whatever you want with the pi groups.
Cool.
But the point is, you can never have more than 3 pi groups, right? You can manipulate them any way you want, but you still only have 3 pi groups. That's all. Right. Okay. So, well, any other questions? Okay. So you got a question?
I was just a bit confused about, like, I know how to find the number of pi groups, but I was not very sure how to determine the number of repeating variables.
Oh, okay. Yeah. So, right. So this is the key number right there.
Yeah.
That's 3, right? So so now you know there's only 6 variables, right? Therefore, remember what the repeating variables are doing for you. Here's repeating variable 1, repeating variable 2, repeating variable 3. You're going to raise them to the A, B, C power, right? Now they're going to multiply those against something, and the something is going to be whatever's left over. So in this case, there's only 3 left over, right? Therefore, well, no, there's only 3 pi groups. Therefore, you can't have any more than 3 repeating variables, or fewer. If I only picked 2 repeating variables, then I would have too many pi groups. If I picked too many repeating variables, I wouldn't have enough pi groups. You see what I'm saying, or
So
I don't know if that's very clear.
we choose, like, we could have done this problem with 2 repeating variables?
No, you couldn't, because you see, right. So you know,
Is it based on how many units
not necessarily. Not necessarily. Let's go back to this number right here, right? Let's hypothetically suppose we had a problem where we had 8 variables. Suppose we had a problem where we had 8 variables and 3 fundamental units. That would give us 5 pi groups, right? Yeah, actually, I think you're right. I think it's going to turn out to be the number of. I think that's correct. Actually, I think what Connor said is correct. I think it's going to always work out to be 3 in this case. The number of fundamental units, I think.
Oh, okay.
I think that's the way it's going to work out. Yeah, I think that's correct. I just didn't quite. So in this case, yes, it works out to be 3. And I think that's correct. If there's only 2, and if there's only 2 fundamental units, then there's only 2 repeating variables. It would be very nice if there's only 1, because if there's only 1, then there's only 1 repeating variable. So you can pick any one. Yes, you can pick. Well, no, you couldn't pick any one. You have to pick the one that has n in it. So, it's also possible to get, well, in some case, perhaps you would have 5 variables and 4 fundamental units. So you'd only have 1 pi group in that case. So in that case, where you only have 1 pi group, then you would have pi 1 equals, yes, or just some number.
Oh, right, okay.
So we don't
That's
have
it.
more repeating variables, right? In that one.
How many repeating variables do you have in this case? I think you would have, what would you have? 4 repeating variables? I guess so. And I think there's several famous cases where this is true, actually. And, this is probably the best possible thing you can possibly get. That's great. Okay. So let's do a problem in detail. let's do problem 2. That seems like a pretty good one. So problem 2, let's see the actual physical situation. Yeah, so the physical situation, we have a ball here, diameter d, and a jet of fluid coming up and hitting the ball like that. Velocity of the fluid is g. Diameter of this jet, I think, it's kind of odd that they said that, but anyway, diameter of this orifice, is it the diameter of the jet, or the diameter of the orifice? Yeah, no, I don't know exactly what d is, actually, it's not clear what d is, but we'll just say there's some diameter here, maybe it's this, I think this should be d right here. So, it should be the distance between the outlet diameter like that. And let's see, what else do we have? We have viscosity, density, viscosity. Oh yes, of course, the ball has some weight. I think that's it. 1, 2, 3, 4, 5, 6, 5. 1, 2, 3. Like that. 1. Oh yes, of course. There's one variable missing, which is the height above that level. So we have 1, 2, 3, 4, 5, 6, 7. 7. 1, 2, 3, 4, 5. Let's see. 6, 7. 1, 2, 3, 4, 5, 6, 7. Yes. So I believe we have 7. So the problem says basically, what is the height? So we turn on the jet, and the ball sort of hovers. It's being levitated by the jet, right? And you want to determine, given all of these guys, what is the equilibrium height? So let's see. What is the dependent variable in this case? H. Yeah. So H is the dependent variable. That has to depend on W, the weight of the ball, the velocity of the jet, the density of the fluid, and the viscosity, and also the diameter of the jet. I have them all here. 1, 2, 3, 4, 5. I'm missing something.
The diameter of the ball.
Oh yes, the diameter of the ball, right. So, right. 1, 2, 3, 4, 5, 6, 7. Well, we sort of, even without doing the problem, right? Even without doing the problem, you can get, again, many answers, but it's pretty clear. Well, let's just do it. Let's not guess. We'll come back later and guess. Units. Some of these units are pretty easy. HL is L. Let's see. D. L, that's good. Capital D L, great. Density, mass over length cubed. Velocity, length of time. Weight is force. So that's going to be M L over time squared. What am I missing here? Mu, yes. M over LT, right? 1, 2, 3, 4, 5, 6, 7. Okay, got that. So that's straightforward. Let's see. Next step, pi groups. 7 variables minus 3. So we're going to have 4 pi groups in the problem. You can almost guess at least 2 of them without, actually. You can probably guess more than 2. I mean, what about H over D? That would work. How about capital D over little d? That would work. You already have 2 of them already without even thinking, right? Then it's pretty clear a Reynolds number is going to show up, right? That's certainly going to show up. And okay, there's another one. But let's kind of work it through and see what happens.
H over D, we cannot use that, right? Because it doesn't have ML and T, all three of them.
H over D is
Yeah.
it?
Is it supposed to have all three?
No. What I was saying was that one of the pi groups could be H over D.
Uh-huh.
Why not?
Okay. So the pi group is not supposed to have all the dimensions?
No, the pi group has 0 dimensions.
No, like all the units.
No, it doesn't.
Oh, okay.
No, only
Oh,
the
I
repeating
think
variables.
Yeah.
No, the pi group has no dimensions at all.
Uh-huh.
None.
Yeah, but we're not supposed to have a pi group where all the dimensions show up, right?
No, not necessarily. No. No, not necessarily at all. No, not at all. No, not at all. Absolutely not.
Okay.
They could, I guess. I guess they could.
It's arbitrary though.
Well, I see two actually.
What's arbitrary?
Like how many
It's
units?
ML over T squared.
In the pi group? It doesn't make any difference at all. As long as it doesn't have any, as long as the pi group has no units, it's irrelevant how many units show up. Doesn't make any difference at all.
I think that's just the units.
They're talking about like, for example, you're saying if it was this and that, then do we have ML and T in the pi group? No, that's not necessary at all. Not necessary at all. No. Pi group is just a non-dimensional number. Period. It doesn't matter how you get it. So without even thinking, H over little d and d over that would work. In fact, we almost know the problem. We almost know the solution of how to do it, but let's do it anyway. Okay. So repeating variables. Got that done. There's 3 repeating variables. Let's see. Well, picking these 3 is bad because that's true. So we're gonna have to do something else. Well, I don't even know. I don't know how to get. We'll just pick something arbitrarily. How about I don't know. Somebody have a suggestion on what the repeating variable should be?
V rho and mu.
Okay, V rho and U. Let's see. I think that works. Yeah, that certainly works.
You can always check, right, to see that they
Yeah.
are repeating that variables. By like,
Well, I know for sure that can't be true, but those are fine because I know the Reynolds number is rho v over mu, and rho v. So it's missing a d. If there was a d there, then of course you could do it. Well, let's just take a quick look and see. V has L and T in it. Rho has M, so we've got M in there, and U has M in there. And yeah, if you take a quick look at those, I think it's certain. You cannot, there's no way you can mess around with these guys to get a non-dimensional number. You can try, you're never going to get it. Why is that? Well, you might be able to get rid of this mass here. But
You would never be able to get rid of one
Time.
of
or L, one of the L's in the time or something. Right. So it's a bit of a tricky thing to pick these repeating variables. You have to really sort of stare at it for a while. Okay. Next step. Let's see what else is the next step. Let's start getting the pi groups. So let's circle. A good thing to do is circle them. V, rho, and U. Now we can. Let's try this one. V, rho. What's going to happen here? This is going to give us a very odd kind of thing. V to the A, rho to the A. This is not an optimal choice because it may not give us exactly what we want, but we'll do it anyway. V to the A, rho to the B, and U to the C will operate against H, right? And then we're going to get N to 0, L to 0, T to 0. Yeah, I can already tell what's going to happen here, but let's do it anyway. Does anybody see what the answer is going to be here?
Yeah, it's
1, 1, and negative 1. That's what's going to happen, right? So we're predicting A is 1, B is 1, and C is -1. We're predicting that. So we'll see what happens. It'll work out. Obviously. So let's do mass first. Mass. This has no mass in it at all. There is no mass. So that would be a 0 plus. Well, let's write down all these units. L over T, to the 8th power, mass over length cubed to the B. Mu is M over LT to the C power, and then H is L to the first power. Okay. So for mass, let's write it down here somewhere. So we have basically nothing there plus B. So we're going to get B from this M over here, and a C from that. And this is not giving us anything at all. That's plus 0 equals 0. Does everybody see how I got that? Okay, that's the first equation. Length. That one's got an A. That will give us an A. This one will give us a 3. Oh, minus 3, sorry. Minus 3. This one will give us a minus 1. That will give us a plus 1. That equals 0. A minus 3 from this. Minus 1 from that. Oh, sorry. Ooh, minus C. Oh my goodness.
And minus 3B.
Minus 3B. Isn't it minus C here?
And then minus 3B.
And minus. Oh yes. Sorry. Right. A minus 3B. C plus 1. Time minus A minus C plus 0 equals 0. Minus A minus C. I think so, yes. Okay, let's see. What are we going to get here? Well, we have to do some algebra. Now, your calculators can do this problem, right? Oh, right? But let's do it anyway, just by hand. B equals minus C. B equals minus C. Wow. Okay. We'll have to deal with these two. Oh, there's obviously a matrix way to solve this problem, but let's do it anyway. B equals minus C. So put that in here. Okay, and then here I get A equals minus. Oh, really?
So A equals B.
So A equals B, and then I can go to this one. So I have A equals B, so B minus 3B, and C is minus A. C.
That you just plug it into the first one, and you know that. Because you know that B equals minus.
So what do you think the solution is?
Yeah, A is 1, and then C is A.
Let's see, that's what we predicted. Okay. I'm not very good at doing algebra. You guys are better at that than I am. Okay. Yeah, I don't bother to do this on a piece of paper. I just use, actually I do. I really shouldn't do it on paper. I should use a computer, but I'm too lazy. So. Okay, but is it, your calculators can do this right away, right? Just put a matrix in there.
Not the one for
Really?
Yeah.
Oh, I certainly will allow you to use it. I don't see any problem.
Actually, there's one version of it, like the 30DX, which is like approved, and you can use it as a solver.
I don't see any problem with that. I mean, if you have one that's got one on it, you want to use it, that's fine.
Just get this one.
What's it called?
So let's
36
see, we
Pro.
get a 0.
It does integrals and
Good. Hey.
This is the whole reason that fancy so you don't have things. Pretty
One.
much. It's like the best one you can get that fits in the group.
I order one from Amazon.
Where they have them at the bookstore.
Yeah, but Amazon.
Minus 3, minus 1 or something.
It'll save you, bro. It'll save you. It does some
I think you
stuff
probably
need
get
for
that. Is that the matrix you get? Something like that. Looks like we've done. Oh, yeah, this one. Yeah, something like that.
Equals -1.
Oh, -1, yes. Right. -1. Oh, yes. Right. Yeah. Wait a minute. Yes, you're right. Okay, so that's the end of that one. And, well, why don't we go on to drag? I mean, these problems are kind of all the same. You know? Once you've done one or two of them, that's pretty much it, right? Just go through the steps. Okay. Yeah, the only time it might, let me just write down the answers. Let me just write down the answer to this one. What is the answer? The answer to this one is this. H over D is a function of capital D over little d, comma, rho d, little d over u, times, comma, w over rho squared. Now, in this, the way we did it, however, we didn't get, what did we get? We got actually, rho d. We get it.
We basically have three diagrams of examples like this one because we use D and D, which are the same as H.
Right, so we get, oh yeah, we had H over here, we get we get this one. Right, rho H over here.
And then we get the same thing with D and big G. And then we have the
Right.
for what
Right. Right.
Right.
Exactly. So, this answer, which I got, is not the same as the answer you would get by using your repeating variables, but who cares? It's the same thing. All we have to do is multiply this by H over D, and we get it. Okay, so that's the answer to that one. And the answer to the third problem, so that's problem number 2. The answer to the third problem is, write that down over here. Third problem, that's the answer to the second problem. Answer to the first problem, the third problem, sorry. The answer to the third problem is shear stress divided by rho u squared is a function of rho u x over mu. Actually, there's a problem. I'll suggest a problem you might want to work on just for fun. Totally different kind of problem. Has nothing to do with fluid mechanics. Just to give you some idea that this doesn't have necessarily anything to do with fluid mechanics. I think this problem, I think we were going to solve this problem in the afternoon class, but we didn't get to it. See what you get if you do this problem. We have a beam and a force F on the beam, and this distance is A, this distance is B, and what you're trying to find is the deflection of the beam at where the force is being applied, let's say delta, whatever that is, and let's see. What are going to be the variables in this problem? Let's assume that the beam has a rectangular, we'll say a rectangular cross-section. A, B, can't call it B, sorry. Call it, what? X and Y. Okay. So the beam, let's say it's a steel beam, some beam, and there it is, there's the cross-section. You have to find, you're interested in delta. That's the thing you don't really know anything about. You know everything else. How can I, just out of curiosity, how can we set this problem up?
Double integration.
Double integration? No. I want dimensional analysis.
Oh, dimensional. Okay, never mind that.
Yeah.
Well,
What is the dependent variable in this problem?
delta.
Delta.
Function.
Okay, so what am I going to put?
F A B X Y.
F, A, B, X, that's not going to solve the problem. What else? What am I missing in here?
Modulus.
Yeah, you already. Yes, we have to put the modulus of the elasticity of the material, and also probably also the modulus of shear, the shear modulus as well, because you are going to have shear forces and bending moments in there. So this is very nice because notice that you do not see any moments of inertia here at all. But it'll all work out. If there's supposed to be a moment of inertia, it will show up in your analysis. Okay, as far as I can tell, that's it. I mean, I can't think of anything else that you could put in that equation. Except maybe the temperature of the beam or something, but. So let's see, what would happen here? We're not going to do this, but you should do it at home. 1, 2, 3, 4, 5, 6, 7, 8. Got 8 variables, and you only have 3. You're going to wind up with 5 pi groups. And a lot of these pi groups are going to be fairly obvious, right? You're going to have a lot of length ratios all over the place. But then you're going to have other things having to do with force and E and gamma.
Professor,
So, yeah.
so with the shear modulus, the shear modulus isn't it a function of E and Poisson's ratio? Wouldn't you have to?
Is it? That's
yeah,
a good question.
because isn't it E over?
Well, okay, I mean, what you're saying is that this is dependent on that.
Yeah, but
But
it's
is
also
it-
dependent on Poisson's ratio.
Okay, well, right, now we're getting somewhere.
Right.
Because if that's a very good question. If gamma is only a function of that and that alone, then you don't need it. But if it's a function of something else, then you have to put it in there.
You don't have to put it in as like you don't have to say that that's a function of the shear modulus.
No, what I'm saying is, whatever this thing is, I don't really care what it is. If it's only a function of E,
Yeah.
then you don't need to put it in.
Oh, okay. But since
But if
it's also a function of
Yes, if it's a function of something else, whatever that is,
yeah.
then you do have to put it in there because it does not just depend on E, right? Because right?
Yeah. So like instead of, for example, instead of putting that, could you just put Poisson's ratio then, as opposed to putting
You
shear modulus?
could, yeah, you could put Poisson's ratio in there, but that's not
Right.
kind of a weird thing to do.
That's only dependent on
I mean,
What did you say?
I think in the case you brought up, Poisson's ratio is actually the dependent variable, but 2 independent variables, as opposed to that one being dependent. Because that's still only on shear and strain.
So are you saying that we should get rid of this one?
No, I'm saying you should keep it.
Keep it, yeah.
But you wouldn't add Poisson's ratio because it's only a function of those two.
Oh, I see. Yeah. So it makes more sense to do this than to do the other thing. Right. So yeah, that's a good problem to do on your own. Okay.
Yeah.
I can't think of anything. Oh well, the only other thing that has to do with dimensional analysis is similitude, which we discussed, right? Let's spend only a couple of minutes on similitude. Only a couple of minutes. We don't want to spend a lot of time on it. Let's talk about it sort of in generality. And then we did a similitude problem. Remember, we did drag on a submarine, right? Back in calculus. We did the whole thing. Okay, so similitude, what are we doing here, folks? How does this thing work? Okay. Similitude, I'll cover this in a couple of minutes. So in the case of similitude, we're going to use the theory to solve a real-world problem. Well, in class we said, okay, we have a submarine, here's the prototype, here's the model, for example. Or another example would be, in the film by Professor Shapiro, he wanted to determine the drag on a balloon, right? A fairly large balloon. But how did he do it? He did it by taking a small sphere and dropping the sphere in glycerin in a balloon. That's how he did it. So let's see, what's the basic idea behind similitude? The first step is, well, let's just make it simple. Let's just say you have 3 pi groups, just to make it easy. You can have as many pi groups as you want. Well, let's put more and more. Let's put 4, 5. Okay, so we got 5 pi groups. So the idea is we have some prototype P, and we don't want to put a gigantic prototype into the ocean or the atmosphere or something like that. We want to make a very, very small model and do something with it. And we want to be able to predict something in this pi 1 group, whatever that is, drag or whatever, right? Okay, so how are we going to design this experiment? What is the basic principle that we're going to use to design this experiment? Can somebody tell me the basic principle, basic idea? Purely mathematical.
Scale it down.
Use a model.
Well, what are we going to do with this equation? There's the equation, and we've got a prototype, and we want to do the experiments with a model. How are we going to use this theory to do that, to design the experiments?
Scale it all down.
Yeah, geometric similarity.
Pi 2 equals pi 2, pi 3.
Yeah, that's it.
All the pi groups
That's
have to be
right.
equal.
It's strictly math. If, we'll just put a big statement here. If, then. If pi 2 equals pi 2, pi 2m equals pi 2p, if pi 3m equals pi 3p, if pi 4m, etc., right? If all these guys, this is p, here's p there. All these gut now, let's get to the bottom line here. If all these 4 equations are satisfied, if you can actually get them to be satisfied in the laboratory, then what must be true logically?
Pi 1m equal to pi 1.
Yes. Then pi 1m must exactly equal pi 1p. Sorry for the bad scribbling. Right. That's all similitude is, right? If you can get all these independent pi groups to match in your laboratory, then you're certain that these, it's got to be true mathematically that these pi groups have to match, right? Therefore, all you have to do is measure pi 1 in the laboratory, and then you should be able to extract out the thing you want, the prediction. We're going to make a prediction about the real world thing, right? And as I said in class, the chances of you being able to match many, many, many pi groups in a real laboratory is pretty slim. So most of the time, you're lucky if you can match 1. You're very, very lucky if you can match 2, because of the various practical considerations, right? For example, in order to match all these pi groups, maybe you'd have to make the liquid, maybe the liquid would have to be tar, or maybe liquid helium or something, or some ridiculous, you could theoretically do it, but it would be impractical. Or maybe you'd have to make the model 1 micron or something. Who knows? Or you may wind up with some ridiculous situation that could be done theoretically, but not in the real world. Right? But that's all that it is right here. That's all that it is. That's the rule. It all comes from this equation. That's really the governing equation. Okay, and we did that problem in class. I think we got, we tried to test a 10-to-1 model of a submarine, remember? Submarine was 10 times smaller, and we were doing it in a wind tunnel, and we got, let's see, the velocity of the wind tunnel had to be 112 miles an hour. And why were we doing it in a wind tunnel, by the way? Because there's lots and lots of wind tunnels, but there's very few oceans, or there's very few water tunnels. There are actually. Yeah, we don't want to test a 100-meter submarine that would cost us millions and millions of dollars. So we do in a laboratory for several thousand, right? Yeah.
So once we get the equation for the model, from that,
This equation here.
yeah, like in the lab, we managed to get the equation for the model. Then we will use those conditions, right?
Well, right. In order to design your experiment, you have to use all of those equations that I listed here.
Yes. Once we get the final answer for the model, from that, how we go back to the
from this equation right here, right? If you measure that pi group, you can measure this in a
They're
laboratory,
just equal.
then you don't know that, well, you don't know, well, you do know what pi 1 is, but there's something buried in pi 1 that you want to know, like the drag.
Yeah.
So if you know this number, then you can extract out what the drag is on the object from this equation, right? You see what I'm saying?
Yeah.
Okay. I think that's, anybody else have any other issues with dimensional analysis? I don't know. Okay, so let's, so there's a drag problem I want to do. Number 3, that's the problem I want to do here. Has anybody looked at problem number 3? Let's do this one. Okay, problem number 3 in problem set number, problem set number, I don't know. Practice problem. So we have a laminar boundary layer. We have 2 completely separate configurations, and it looks something like this. Here's configuration A. It's kind of an interesting problem. It's kind of tricky. So we have 2 completely different configurations. A, B. These plates, let's see. This is 3 inches on a side, 3 inches by 3 inches. This is 3 inches by 12 inches, I guess. Each of these plates is 3 by 3, and water is flowing at a speed of 3 feet per second. 3 feet per second. Oh, the temperature is okay. Temperature 70 degrees, that's not a good thing. Okay. So the idea then is, and we're also going to assume that there are laminar boundary layers here, not turbulence. So the question is, which one of these configurations is going to give us the largest drag, or the largest or smallest? Which one's going to give us the largest drag, right? We're going to neglect this. There's a string connecting these 2 guys, and really the string is going to be a tiny thing. It's negligible, but the distance between this one and that one, let's see, is not given in the problem. The assumption is that this one is very far from that one. I don't know exactly what very far means. Maybe 5 or 6 times the width or something. So this one is very far from that one. And each one of these guys is very far from its neighboring one. And the only thing connecting them is a very thin wire or something. In this case, all of them are stuck together. Okay, so how are we going to do this? How are we going to calculate the drag? Let's see. Well, I actually have a solution here, but I'm going to let you guys work it out. I want to go over the basic idea, and how we're going to do this. So I'm not going to do the whole part. I want you guys to do it, or at least to give me some ideas on how to do it. Let me just state what the problem is. Here, we're going to get drag sub A, and here we're going to get drag sub B. So the question is drag A greater than drag B, or is drag B greater than drag A, and, yes, or that, or are they equal? I don't know which one of these is true. And then also, it would be nice to know what the drags are in actual numbers. Because if I can do that, then of course I can solve the problem right away. Okay, let's not assume anything. Let's just work out the problem. I'm pretty sure you probably have an idea what the answer is, but let's just work it, do it anyway, even if you think you know the answer. Okay.
Professor,
Yes.
springs, they are not rigid, right? Like, no
Rigid,
rotation or anything is allowed,
well, you're looking down on it.
right?
What difference does it make if they're rigid or not? I mean, they're just,
I mean, they can move.
well, I mean, there's gonna be tension between them, right?
Yeah.
There's gonna be some tension. So they're not gonna be wiggling around.
Okay, so.
I hope not. Yeah, I mean, this is a pretty, right? Now, if we look at one of these plates from the side, it's gonna look like this. And the flow is going over the plate, and the boundary layer is growing over that plate. Right. And what else can we say? Well, it's actually growing on both sides of the plate, symmetrically. Okay, so you tell me how I'm going to solve this problem. What do I have to do? We have a long time, we have a whole hour, so I'll let you guys just, worry for a whole hour how you're going to solve it. I don't want to do any more work. No, I'm going to do it. It's your job. How are we going to do this? I don't want you to guess about what the answer is because that's not relevant. I want real hard numbers. I don't want any guessing. So let me draw a picture. So here's a picture of this one. And now this guy is very, very far downstream, way out there. Right. So the idea is that this guy is relatively unaffected by that guy.
So A is effectively 4 times the drag on one plate.
Yeah, let's just call this 1, 2, 3, 4. We'll call this 1, 2, 3, 4. Identical plates. This guy is very far from that guy, so the weight from number 1 does not really do anything to this guy. You can consider them to be all being attacked by U infinity. So there is going to be a weight behind this one, some kind of disturbance, but we're pretending that this disturbance comes to an end, and then this guy is now equivalent to this guy.
So drag A should just be 4 times
Right.
1.
Right, exactly. So So in this problem, you got the first part right. The drag on this entire configuration is going to be the sum of the drags. That would not be true if these two guys were close together. That would be a different story. Because then that would be very complicated. Because then we would have to understand how the weight forms, and that's way outside anything that we could do easily. So yes, that is correct. In configuration A, you're right. The total drag in configuration A is going to be D1 plus D2 plus D3. Whoops. Well, we'll just say 4 times D1, right? Just 4 times D1. And I don't want to talk about this one. Right. So that's correct. Okay, any ideas? So far, you got a pretty good idea there. Right. They're independent. How about writing down the equation for the shear stress or the drag on a flat plate boundary layer? We know the exact result, right? The exact result is, let's see if can I use this blackboard over here, or
Oh yeah, sure.
am I getting?
I can adjust it. Yeah, that's good actually.
Okay.
It's perfect.
The drag coefficients, C sub f for a laminar boundary layer is tau wall. We're going to have to discuss this. Exactly what this is, exactly how to do this. Okay, now I'm going to ask you some questions about this equation. Let's see. First question is, where did this equation come from? Maybe that will be on the multiple choice. Who knows? Where did it come from? For a laminar boundary layer. Laminar boundary layer. Laminar, not terminal. A laminar boundary layer. Let's go back a second. What exactly is a laminar boundary layer anyway? Let's start from the very beginning. We might as well. We have time. We have time to drag this conversation out. Okay. Glad you guys appreciate that. Only joking. I'm just joking. I'm thinking of quitting my job and becoming a stand-up comedian, right? I'll just talk about fluid mechanics all day and get people to laugh at it. That would be quite an accomplishment to get people to laugh at fluid mechanics. That would be something. Anyway. I have to be a pretty good comedian to do that. Okay, so what is a laminar boundary layer? Tell me.
Slow-moving flow with heat momentum transport at the micro level.
That's pretty good. That's pretty good. Yes, that's very good. You got the concept correct there. Heat and momentum transported at the micro level, at the molecular level, correct. And when you say slow, yeah, you're more or less right there. But the idea then is that all the layers are moving without mixing with one another, right? There's no mixing going on. It's like one layer is moving this way, the other guy's moving. They're just moving past each other. But they are communicating with each other through molecular diffusion, right? So I think you got about 90% of the correct answer. That's correct. Okay, so we got this laminar boundary layer. Where did this equation come from? Did it come from, I don't know, an experiment? Did it come from some theory? Did it come from where? Let me back up again. Is this equation exact? Exact meaning within like 1% of the correct answer, or is it just kind of a hand-waving answer that maybe way off? It's exact. Yes. How do we know it's exact?
That was experimentally determined.
No. Close. Black, you're not close. There's only two possibilities. It was either not experimentally determined or experimentally determined, and you guessed wrong. So therefore, the answer is it came from an exact theory called the Blasius theory, right? And is this an analytic solution or is it a numerical solution? Which one? If you're reading the book, you know. Or you're reading my notes, you know. These are all questions that could pop up on the final.
What was the question?
The question is, was this result obtained from an exact theory, or did we have to do some numerical integration to get it?
Experimented. It was found by experimentation.
No. He said that, and I said it was wrong. No, laminar, not terminal. There's an exact solution for the laminar boundary layer, right? It's called the Blasius solution. It's called the Blasius solution, right? But my question to you is, this is an exact result, as he said. But my question is, how do we get this result? We said this in class. It's in your notes. It's in the book. Numerical. That's it. Numerical. It was done numerically. And because there is no exact solution to this problem, but you can get very accurate numerical solutions. Okay, here's another question. Why is it that we cannot get an exact solution to this problem? Why do we have to do numerical work to get it? Glad we're going over this. I can see where some of the weaknesses are. Why do we have to use numerical methods in order to get this equation? Why can't we just simply solve the equation with a boundary layer? Say that again? Yeah, but that's not the real reason. The real reason is that because the Navier-Stokes equation for this problem, you have an answer?
No, I was just saying it. I was whispering it to Mike because I wasn't totally sure.
Well, what was your guess?
I was just going to say, since it's derived from Navier-Stokes, and Navier-Stokes doesn't really have a full answer, we kind of get an approximation of it.
Yeah, that's correct. Because the Navier-Stokes equation is a nonlinear partial differential equation. And there are no, generally speaking, there are no solutions to these nonlinear equations. It's because of the nonlinearity of the equations that we can't get exactly. But this solution is it's extremely accurate. We know that. All right. we're getting off the subject. Okay, so we've got this equation. What good is this equation? What is it telling you? Why do we care about this equation? It's directly related to this problem, but what? Okay, can somebody please tell me what exactly is tau sub W? Correct. Let's draw a picture. Here's a flat plate. Here it is. Here is the origin of a coordinate system. Here is x going that way. Flow is going this way, u infinity, some velocity. So the question is, how would I draw the shear stresses? What are the forces acting at this point? Boundary layer is growing. What are the forces acting on the plate at that point? Well, the plate, let's make the plate have some sort of thickness. Have some thickness. Flow is going this way. What stresses are acting at that point? Shear stress. In which direction does the shear stress act? Parallel to the plate, right? So we can put a little tau there. And of course, we do have pressure pushing down, right? Okay, but we have a distribution of these stresses, correct? They're distributed, and let's draw a picture of it. Here is x. Here is the shear stress. W just means shear stress at the wall, literally, physically at the wall, not somewhere up above. So what is this picture going to look like? Can somebody tell me? Is it going to go from 0 here to there? Is it going to go from high to low? Is it going to go straight across? What is it going to look like? High to low is correct. It's going to start out basically nearly infinity. Well, we'll get to that in a second. And it's going to decay. Right. And how do we know that? Well, you sort of know that, but how can we use this equation to tell us that? What is the Reynolds number sub x? How is that defined? Right. U infinity x over the kinematic viscosity is correct. So therefore, we see that the x is showing up in the denominator here as a square root, right? So that means as x goes to infinity, then this thing's going to go to 0, right? And however, when x is close to 0, it's infinite, right? So it's really infinite here at 0. Now, does anybody really believe that it's really infinite? Is it really infinite, or is it just...
It's really high.
Well, of course it can't be infinite, right? So does that mean that this theory is incorrect at x is 0? Yes, it does, because it doesn't correspond to experiments when x is 0. This theory is only valid if you are at least one boundary layer thickness away from, you've got to be some distance away from leading edge for this theory to be correct. Right, very close to the leading edge, it's not going to be correct. But that doesn't matter. It turns out it's a very small error, actually. Okay, so we see that the shear stress is infinite here, or very high here, and decays to 0. Can somebody tell me, why does it decay to 0? What's going on physically? Why does it decay to 0? Let me draw the boundary layer profile here. Here's the boundary layer. What does this line mean here? I'm drawing a line. What does that line represent? Yes, it represents the point at which the velocity is about 99% of u infinity. So let's draw the boundary layer profile here. It's u infinity here, and then it goes to 0 there. Correct? No slip condition. Right? Okay. Now let's draw a boundary layer profile here. This is u infinity over here. This is u infinity over here. If I take a look at these two velocity profiles, can somebody tell me why do these velocity profiles result in a shear stress distribution that looks like that? Yes, exactly. If we're close to the leading edge, as you just said, the boundary layer thickness is 0. Therefore, the velocity theoretically, according to this thing, would change from 100 miles an hour at the free stream to 0 in 0 distance. That would be an enormous shear stress, right? Whereas way out here, the velocity changes are very, very gradual. So you get almost no shear stress way out there, right? So as you can see already, we're beginning to understand this problem after thinking about it very carefully, right? Okay, so now that we've gone over the basic idea here, what's the next step? We literally want to calculate dB. We literally want to calculate dA. We want to get real numbers, not just some hand-waving, silly stuff. What are the units of the shear stress? Tell me. Yes, newtons per meter squared, right? That's what we want. How many newtons per meter squared are we going to have on this thing? Let's start with an easy one. How can we calculate the drag on this guy? Tell me.
On which one, the bottom one?
The bottom one, yeah. How are we going to do that? Better actually do it.
Are we giving kinematic viscosity?
Yeah, we assume you have all that.
So can we just say that the x is 12? Oh, you're right.
Yes. Okay, let's talk about that. To get an accurate idea. So to get an accurate estimate, what are we going to do here? We have a very, very large shear stress at the leading edge. I can't draw a large number, but look, that's very large. Smaller, and it kind of disappears, right? So that means that the shear stress is a function of x, right? Well, we actually know what it is. It's given to us by this result. Right? So we know that the shear stress depends on x. It's very large, and then decays. So if I want to calculate the total force on this plate, how am I going to do it?
Take the interval, the distance.
Take the interval. The interval of what?
Distance. Of the base.
So let's just take a small little sliver dx, right? Now let's look down on it. Let's look down on it. If I look down on the thing, I'm going to have a very, very small strip, right? The strip will have a width of dx, right? And the length of the strip is what? What is the length of the strip? 3 inches, right? Because we're looking down on the plate. 3 inches, right? We'll just call it W, just to get it. So this is going to be W. So what is the area of this tiny little strip here? Actually, it's not tiny, it's just very narrow. Wdx, right? That's going to be the area of the strip. So if I take stress and multiply it by area, then I will get what? dF, a differential force, right? I'm not going to get the total force, I'm just going to get the small force that's pushing the plate forward, right? Now I can integrate it. I've got it properly formulated, so I'm going to integrate this thing. W is a constant, right? So number dx, that equals total force. I'll just call it F sub A. Maybe I should call it, which is the same as dA actually. dB, oh sorry, oops. dB, oops. That's going to give me a force, which is in fact the drag on the plate. Actually, this equation is not quite right. I have to do something to it. What do I have to do? Yeah, that's true, but something else. Plane has 2 sides. I should multiply by 2. Let's not multiply by 2, which is too confusing. Let's ignore that. So we're going to go from x equals what to x equals what?
0 to 12.
0 to 12, correct. We'll just call it L sub b, which is going to be 12 inches. Okay, now we can do the problem. Because now we know what this thing is. Let's write it down. Tau is equal to 1/2 the density times u infinity squared times a, well, what is this number here? I don't know what to call it. We'll write it down. 0.664 times x to the minus 1/2, right? It's got to be x to the minus 1/2, and and u infinity over nu. I think it's got to be u infinity over. Let's get rid of this. U infinity over nu to the minus 1/2. Wait a minute. Yeah. U infinity over nu to the minus 1/2. And x to the minus 1/2, right? Right? Okay. Any problem with my algebra? I think, yeah, that's correct. Now, all of this stuff is just a constant, right? So let's just call it k. In fact, on a test, you should probably, that's exactly what you should do. Just call it a constant. Calculate it anytime you like. Times x to the minus 1/2, right? So now let's do this integral. So now this integral is going to be equal to the integral from 0 to L sub b times a constant times w, which comes from here, times x to the minus 1/2 dx. And I can take this kw outside, I don't need that anymore. Kw times the integral from 0 to LB. And I can do that integral, that's kw times x to the 1/2 divided by 1/2, right? That gives me, I think that's right. That gives me 2. That I went from 0 to LB. So I get k times w times 2 times L b to the 1/2. And that is the total drag d sub b. I don't know if I made any mistakes there. So what does that turn out to be? I didn't actually calculate the number. I should have. Oh, yes, I did. No, okay, we'll come back to that in a second. So anyway, you can easily calculate this, right? We'll come back to that in a second. Okay. Now, so we've got an expression for that. Maybe one of you guys can calculate it if you want. Any questions about that?
So for the exam, could we just leave it as k instead of dragging it along?
Yeah, you can leave it that way. But unless you need to use it as a comparison to something else, you're going to have to calculate a real number.
Okay.
Yeah. Okay, now let's go to case A. So in case A, what is the drag going to be?
Do we follow the same procedure? We multiply by 4.
Well, since we're saying that they're independent, we can calculate the drag on one and just multiply by 4. So the drag on the total configuration is going to be 4 times the drag on unit number 1. And that's going to, we know what that is. That's 4 times, let's see.
Shouldn't it be the same thing with different integration?
Yeah, exactly. It's going to be the same thing with different rooms of integration. That's right. And so this is going to be the thing that's going to change, right? Right. So it looks to me like we're going to have to put a 4 there. Because we have 4 of them. I think you're going to get 2 kW. That doesn't change, right? But here, I'm going to get LB over. I'm going to get
You're gonna get 3.
LB over 4, right? Is that right? Okay.
Okay, would LB over 4 be the same as 3? Because LB in that is 12.
What do you mean by 3?
Like 3 inches, or is that?
Yeah, because LB is 4 inches. So
Oh, yeah, it would be, right.
Oh, okay, all right.
Right. So that's okay. So now that's interesting. Aha. Now, without any calculating any numbers, we might be able to actually solve this problem. So we get 4 divided by the square root of. I'm taking the square root of 4 here and putting it over there, right? And then what's left over? 2 kW times L. I hope I'm doing this right. You have to check me. But this is D sub B, right?
Twice.
Yeah, twice. Therefore, this is 2 times dB. Is that the result I had last time? Yes, it is. Yeah. So we were without actually calculating any numbers, we were able to get the answer. So that's nice. That's a nice trick. So let's see. Does that make any sense?
Yeah.
The drag. This one's going to have a higher drag, right?
which one? Top one. Yeah.
But okay, we already solved the problem. But why? Why does the top one have more drag?
More surface.
Oh,
No, it doesn't have more surface area. Same exact surface area.
Because the drag is lower the longer along the farther along you get lower drag.
Yeah, sort of. Right. Right. Well, it goes back. Remember the picture we had in the beginning? Yes, exactly. That's exactly right. Right. You're going to have this repeated. This is what's going to happen, right? On the top one, you're going to get instead of that. Or it's right. So it's that leading edge effect that's getting you, basically. And it's kind of interesting. I don't know why it works out that way, but it works out that this one is twice that one. When I look at the picture, it's not obvious to me that that would be true. Maybe it is obvious. I don't know. I don't see it as being obvious. Right. So I think that's a very good problem. And by the way, I just want to remind you guys of this issue here. Well, so remember, for the turbulence boundary layer, TBL, let's do another calculation, but let's write this down first. There is also an expression for the shear stress. Let's talk about this. This will allow us to talk about turbulence a little bit. By the way, in the laminar boundary layer, there's also an exact equation for delta over x. Remember this famous equation. The boundary layer thickness over x is 5 over the Reynolds x, right? Let me also tell you what many students do, which is wrong. If I ask you to calculate the drag on one of these shapes, what students typically do is they calculate the shear stress somewhere, and then they multiply by the area of the plate. That's obviously wrong, right? Or what a student will typically do is take the plate, calculate the shear stress at the end of the plate, and then multiply by the area. That's not correct. You've got to integrate, right? That's obviously wrong. You might get an accurate answer. Actually, I don't really know. Maybe if you took anyway. You can't do that, right? You've got to integrate. Okay. Here's the equation for the turbulent boundary layer. And here's the equation for the laminar boundary layer. You can see they're very different. It's an equation for the same thing. Here we see square root of the Reynolds number, and here we see Reynolds number to a very small power, right? Which basically means that, well, let's go back to this. Let's talk about this for a second. There's also, of course, this equation. Delta over x equals 0.382. And you don't have to memorize these equations. If you need them, they'll be on the test. Reynolds number, x to the 1 at 1. So this will give us a chance to talk a little bit about turbulence. And let's do that. So we have these two sets of equations. Let's write the other one down just for reference. Laminar boundary layer, tau sub w over 1/2. Squared is 0.664. Square root of the Reynolds number. Boundary layer thickness. We'll do a calculation for fun. Okay, so now we can compare the directive. And the biggest difference here is, of course, this power of 1/5, right? Notice also this equation, and this one, and this one, and this one. They are of the form pi 1 is a function of pi 2, right? They are in fact, you could obtain something like them from pi analysis. However, from the pi analysis, you would only get this. You would get tau over, well, it would be a 1/2 there, but it probably wouldn't show up. I should put it there. You would get that this is a function of u infinity x over nu. That's exactly what you would get, right? But now you can see what happens, how you finally get to use this equation, because you would go into a laboratory and you would determine the function. What does the function, what is this function? Well, it turns out to be, for turbulent flow, 0.382 divided by the Reynolds number to the 1/5 power, right? So this is literally the functional relationship between that and that, obtained by an experiment. Okay, let's get back to this discussion. Now you notice something interesting, that in the turbulent case, this is a very small number here, 1/5. And if you want to sort of wave your hands a little bit, maybe you can put a 0 there if you were trying to make an approximation, which is probably not too bad. Then what would you get? You get that the drag, the shear stress, over 1/2 rho infinity squared is approximately, or at least somewhere in the neighborhood of, some number, some constant. So as the Reynolds number gets really high, the turbulence gets to be strong, the Reynolds number doesn't have that big of an effect anymore. Which makes sense, because after all the mixing is being done by turbulent mixing, not by viscosity, which is a molecular process. So that's the first thing you would see. Here's another problem that you should think about regarding drag on a flat plate. Here's a flat plate. It's kind of a tricky problem. You might want to think about it a little bit, how to do this problem. Here's a flat plate. Now, initially on the flat plate, you're going to have a laminar boundary layer, which is called that LDL. And at some point, if you put perhaps some roughness up here, trigger the turbulence, this thing will rapidly become turbulent and grow much faster. Very, very, very strong turbulence will develop. So now the question is, how would you calculate, it's kind of a tricky problem, how would you calculate the drag on that plate suppose you actually know, well, actually, the transition between laminar and turbulent is not so abrupt, but it's fairly fast. So we can just call this point the transition point. We can approximate that from this point to 0, it's laminar, and from this point to L, it's turbulent. So how would you calculate the drag on this thing?
Do we just integrate for laminar up until xt and then turbulent afterwards?
Yeah, well, that's close, but not quite, right? It's a little bit, you're close, but it's a little trickier than that because you cannot use this equation, this one, from here to there. It's not quite accurate because this equation is only valid if the turbulence started at x equals 0, right? Therefore, in order to do it, you'd have to calculate the virtual origin of the turbulent boundary layer, which would be there.
And you can subtract.
Yes, and then you would calculate the drag from here to there, and then you would subtract the drag from there to there. Or so, no, the other one. Did I get that right? No. You would calculate the drag from here to there, and then subtract the drag from here to there from it. Because this is a virtual origin. Does everybody see what I'm talking about here? So this is a bit of a tricky problem, right? I'm not saying it's going to be on the exam. I'm just telling you. You should kind of think about it, right? Think about how to solve it. Okay, next question I have for you. We have a lot more time left. What do you know? Why is the drag in a turbulent boundary layer greater than the drag for a laminar boundary layer? Why?
Because it doesn't decrease as rapidly. Like in the laminar, it decreases rapidly.
Yeah, so you're talking about qualitatively
Yeah.
what the profiles look like, right?
Yeah.
For a turbulent boundary layer, this is a very crude approximation. It's not really like this, but a crude approximation. Basically, the velocity profile is very flat. It's very, very flat. And at the wall, very close to the wall, it would finally go to 0 very rapidly, right? That's kind of what you're saying, right? Whereas over here, it's sort of like very, very smooth or very slowly varying. Well, actually, it might go like that, very, very slow, like that, right? So what you're saying is that it is observed in experiments that the turbulent boundary layer is very, very flat, whereas the laminar boundary layer is not as flat. But that doesn't really explain it, right? You're just telling me what is observed experimentally. So the question is, why is this one so flat? And why is that one so not flat? Kind of smoothly curved and not so rapidly varying.
Because of the mixing, right?
Correct. Mixing. Yes. Turbulent mixing, you got it. Turbulent mixing itself is taking high velocity stuff over here and dumping it towards the wall to smooth out the velocity profile. Of course, you also have low stuff going up as well. So you have very rapid mixing across the layer. In this case, not in that case. In this case, there is no mixing going on. There's only diffusion that's creating this much smoother shape. I shouldn't say smoother. This much less flat shape. I don't know how to describe it. More gradual. Well, this would be a uniform type of shape. This would be a more gradual transition from infinity to 0, basically. So mixing is very important. Now let's go even further than this. We're talking more about qualitative stuff here, because
I just had questions about the two equations. Like the one for the laminar boundary layer, it's exact, right?
yes,
But one for the turbulence is not.
correct. This is an experimentally determined, right?
And that one can be used from any point to any point, the laminar one, right?
What do you mean by any point? Well, you can use it from
Like I
No,
don't need
no,
to
no.
start from 0.
no. With this equation and that equation, these equations are only valid from x equals 0 onward.
Oh. Why is that though? Like,
That's just the way they're defined, that's all. I mean, how else could they be defined? I'm not quite sure. I mean, if you want to offset it, but I don't. Yeah, it's valid for x equals 0 all the way to infinity. Both of them. Now, the reason why we have to do this in this problem is because the turbulent boundary layer occurs before the laminar boundary layer. It doesn't go the other way around. So therefore, we have to track back where. Well, we're imagining that the turbulent boundary layer started over here, even though it didn't. Because we have to somehow subtract out that extra drag. Somehow take that into account. It's probably going to be a very small effect anyway. Okay, let's see, what else can we talk about here? Yes, so we see this very flat profile here. And in class, we discussed this. It's in your book. It's in the films. It's everywhere. There is a very specific kind of stress that is generated in a turbulent flow that causes this profile to be very flat. Does anybody have any idea what? And increases drag. What is this statistical quantity? That we're talking about in class. That's in your book. That's in the movies. It's a statistical quantity associated with turbulence that's directly associated with increases in drag, in shear stress. Anybody know? I emphasize it, I think, a lot in class. A lot. What do we call this? U prime, B prime, phi. Reynolds stress. And it's this correlation between these two velocity components that is the direct cause of increased drag. So the question here would be, near the wall over here, in this turbulent boundary layer that we have, let's see, U prime, B prime, bar, is it less than 0 or is it greater than 0? Which one?
Near the wall.
Yes, very close to the wall, right around here. Very close. Yes, it is less than 0. That is correct. It is less than 0. Reynolds stress is less than 0. Why is that? We talked about that in class. Because if a chunk of fluid over here jumps up to a higher level, right? This guy is moving slower than the particles up here. Therefore, when it gets there, it's got a negative, essentially a negative U prime, because it's traveling slower than its surrounding neighbors, right? However, it has a vertical V. Therefore, negative times positive is going to give you a negative correlation. Right? And the same thing happens when a blob goes that way as well. This guy is traveling faster than most of the guys over here, so once it hits there, it's going to give you a positive U prime. But the V is negative, therefore you're going to get another negative number. So the Reynolds stress is definitely going to be negative near the bottom wall. Okay. And of course, you can understand this. It is in fact mixing. This is really what's going on here. It's mixing. Let's see. What other concepts can we talk? I have an idea. Let's just do this little calculation for fun, just for the heck of it. Get some sense of what's happening here. Why don't we do this? Why don't we calculate? We have a laminar boundary layer here, and then we have a turbulent boundary layer. What does that look like? Much more rapidly developing boundary layer. Okay. So here we are at. Now you're going to have to do some calculations. Let's say 10 meters from leading edge, and we'll do water. Try water. So let's calculate the boundary layer thickness in a laminar boundary layer, 10 meters from the leading edge, with a velocity u infinity of 1 meter a second in water, just to see what kind of number we get. So laminar, for the laminar boundary layer, delta is going to equal 5 times x times the square root of the Reynolds number based on x, so it's u infinity x over nu. Notice something very important. This Reynolds number is not one number, it depends on x. It's 0 over there, and it's much larger over there, right? So, okay, get that right? 5 times. No, what did I do? It's x times times u infinity x over nu to the minus 1/2, right? Let's find out what it is. Let's see, we're talking about water here. What, I know, let's look this up just for fun. What is the kinematic viscosity of water? I think I know what it is, but if somebody look that up for me, kinematic viscosity of water. Is it 10 to the minus 5 meters squared per second? I'm not sure. It's either 10 to the minus 5 or 10 to the minus 6. What is it? Ten to the minus 5 or 10 to the minus 6. I think it's
8.9 times 10 to the negative 4
10
pascals.
to the minus 5. Is it? At room temperature.
I got 8.9 times 10 to the negative 4 pascals.
No,
Wait.
kinematic viscosity, not viscosity. Kinematic. It should have units of meters squared per second. I think I have it written down somewhere. Where is it? I thought I wrote it down. I know what it is. I just want to. Oh, I've got it. Okay, I've got it. The answer is, or something close to the correct answer, is that the viscosity, the kinematic viscosity of water is 10 to the minus 6 meters squared per second. Yeah, that's right.
Yeah, I looked it up, that's right.
Yeah, something close anyway. Okay, so let's say we've got 1 meter a second here, and we're 10 meters down. So let's calculate delta. Delta is 5 times 10 meters times, what is the Reynolds number? Reynolds number is going to be 10 times, 1 times 10 divided by 10 to the minus 6 square, minus a half. I don't like half there. Minus a half, right? Yeah. So it's minus a half. What is that going to be? The Reynolds number is 10 to the 7th. What is 1 over the square root of 10 to the 7th? Is that right? 1, 10, minus 6, 7. 1 over the square root of 10 to the 7th. What is that? Anybody know? I can't calculate that one in my head because it's not an even number. It's 1 over the square root of 10 times 1 over, what's that, 10 to the 3rd. I guess it's about, what's that, about 0.3 times 10 to the minus 3. Can somebody verify that for me, or am I doing this?
3.16 times 10 to the minus 4.
3.16. 3 times 10 to the minus 4. Good. Yeah, that sounds right. Okay. So that gives me, let's see, that's going to be 5 times that, 0.3 times 10 to the minus, we'll just use 3. 3 times 10 to the minus 4. So the answer is 15 times 10 minus 4 meters. Okay, let's see. Meters. That's 0.0015 meters, right? Okay. How many millimeters is that? 1 point, I think, if I'm right, it's 1.5 millimeters.
What's the X
Did I goof up? What?
At which X?
10 meters.
Okay.
10 meters. That's very long. And 10 meters is, that's long. It's 30 feet long, right?
Oh, how did you get the 1 over root 10 to the 7? Where's that from?
It's Reynolds number to the minus a half, right?
Right.
So U infinity is a meter a second, X is 10 meters, and kinematic viscosity is 10 to the minus 6. So that's 10 to the 7 to the minus a half.
Oh, wait, is that the answer of it?
No. This. Let me get rid of this. So I'm trying to calculate, just separate these two things.
Oh, okay.
Right. This is supposed to be that. If I did it correct, this thing, whatever this is 1 over the square root of 10 to the 7th. Right? Because this is 10 to the 7th, right? And there's a minus a half here, so it's 1 over the square root of 10 to the 7th.
Okay.
Which is 3 times 10 minus 4. So that's that's interesting. So let's write that down. The boundary layer thickness at 10 meters for the laminar boundary layer is 10 to the it's 1.5. I think. Correct me if I'm wrong, but I think that's it. That seems awfully small to me, but that's what it is for water. Very, very small. 1 point. That's like really, really, really small. Okay, let's do the turbulent boundary layer. I hope I did the calculation right. I think I did. Did I do it right? It's obviously a lot of scribbling here, so I can easily have done it wrong. Okay, but I think it sounds right. A little smaller. Let's do the turbulent boundary layer. Here it is. So here we're going to get delta is going to equal x 0. Oh, wait a minute. Did I include? Oh, yeah, I got the 5. Okay, 5 here. 0.3. I was hoping I missed 5 here. 0.382 times x times same Reynolds number to the minus a fifth. So that would be, what the heck is that? That's 1 over the 1/5 root of 10 to the 7th, right? So let's write that down. 0.382 times 10, because it's 10 meters down. What is the 5th root of 10 to the 7th? I don't know. I could guess. But what is it about? I can guess it's probably around 0.01 or something. Can somebody do that?
Would it be 10 to the minus 7?
Did I goof up? No. Reynolds x to the 1/5. So the Reynolds number is 10 to the 7th.
Oh, yeah.
1 over the 5th root of, what is that, 5th? Yeah. What is it? What's the notation here? 5 or something?
Yeah.
The 5th root of 10 to the 7th? Anybody have a number for the 5th root of 10 to the 7th? I don't know what would that be. That's about, I don't know. Probably close to
25.118.
25. This is 1 over 25, roughly.
Roughly, yeah.
Okay, so somebody calculate 0.382 times 10 divided by 25. Yeah, that sounds right, because, yeah, that does sound right. 0.382 times 10 times divided by 25.
0.152.
What did you get?
0.152.
152? Okay, we'll just say 1.15. So that means that for that one, 0.15 meters. That's, how many centimeters is that? That's 150 centimeters? 150 centimeters, meters, 150 millimeters, correct? Wow, it sounds right to me, but I didn't expect it to be that much bigger. Yeah, wow, what a difference that is. Did I goof up? Let's see. You might be right. Who knows? Let's see. Let's go back. What was the equation here? I could easily have goofed up. Delta over x is 5 over square root of Reynolds. So, oh, maybe you're right. Maybe I didn't multiply by 10. You're right. I think you're right. Yes. Okay. That explains why it's so small.
Good job, Eric.
You're right. You're right. Absolutely. That's a good one. Good see that, but I lose 10 points. Yeah, you're right. It's 10 times bigger than this. Oh, it's okay. That's easy to fix. It's 15 millimeters. Okay, that's better. 15 millimeters. Right. What is that? 1.5 centimeters? Yeah, 1.5 centimeters. So, but yeah, so it's still 10 times. There's a 10 times difference here, which makes sense. Turbulent boundary layer is mixing rapidly, and this equation presumably is correct. Naturally, this equation that we have here is only going to be true for a perfectly smooth boundary layer, a perfectly smooth flat plate, like no roughness, nothing, just like smooth as glass, right? Which is in the real world, this equation is going to have to be modified. Let's see. Let's talk about one more issue. Any questions about this? All right. So let's talk about one more issue having to do with turbulence. Before we go, what do I want to talk about? Yes. Okay. Here's an interesting problem. So here's a flat plate. Same story. And we have a laminar boundary layer growing on it, right? Now, this boundary layer is very, very small. As you saw, I mean, if this is x from there to there, and that is delta, then we know that boundary layer theory, if you believe it, it's only valid when delta over x is much, much less than 1, right? That's the whole point of boundary layer theory. If the boundary layer thickness is of the same order as x, it's not valid. So, my question to you, I have several questions. Where on this flat plate is this assumption violated? At the leading edge. Correct. Correct. It's not valid at the leading edge. That's why you get such a crazy answer. Because the whole theory was not developed for the leading edge. The fundamental assumption, boundary layer theory. This is it right here. I'll say that again. This is the fundamental assumption. Now, tell me something. If this is true, what can I say about the Reynolds number? Is it large, small, or what? Any boundary layer. Large, yes. The only way that this can be true is if the Reynolds number is large. There's no other way. Look at the problem we just did. The Reynolds number was 10 to the 7th. If we calculated a Reynolds number of 1, then all these equations are really not valid at all. Or they might not be very, very, very useful unless you were very, very far downstream. Okay, so that's very important. The next question is this. So we got that situation figured out. What else? Yes. When we're outside the boundary layer, right out there, way out there, what kind of a flow do we have here? Well, let me back up a second. When we're inside the boundary layer, are viscous forces important or not? Yes, absolutely. Because the only reason why the boundary layer exists is because of the no-slip condition, right? And the no-slip condition is directly related to viscosity, correct? Therefore, obviously, viscous forces are important in the boundary layer. What happens if I'm way out there? Are viscous forces important out there or not? No, they're really not important at all. So here we've got a viscous flow. It doesn't matter whether it's turbulent or laminar, it's a viscous flow, right? Now, way outside the boundary layer, even if the flow in here is turbulent, the flow out here is not going to be turbulent. So you tell me, what kind of flow do we have out there? We spent 3 weeks on it. What is that flow? Yeah, but how does that flow, how do we classify that flow? Potential, yes, it's a potential, correct. Way out here, it's a potential flow, correct. And very, very close to the wall, it's a viscous flow. So therefore, what is a boundary layer? A boundary layer is the region separating the wall from the outer potential flow. That's what it is. Repeat that to yourself 10 times. A boundary layer is the thing that transitions, that gives you the transition from the wall to the outer potential flow, right? That's what it is. There has to be some kind of transition, and then that's exactly what the boundary layer is doing for you, right? Okay, next question. We have this potential flow out here, right? Can somebody give me some idea of, if I have a pressure probe over there, and I go straight down over here to point number 2, can somebody give me some idea, what is the pressure difference between these 2 points? The pressure difference, what is it? What do you think it is? Do you think it's big, small? Yes, it's very close to 0. Not exactly 0. Close. Because this boundary layer is very, very, I just proved it to you, right? At high Reynolds number, that boundary layer is tiny. So the outer flow is virtually straight streamlines out here, right? Therefore, from the Bernoulli equation, if the velocity here is the same as the velocity there, then the pressure is virtually the same, correct? Therefore, if the incident flow is parallel to the boundary layer, then what is the pressure gradient inside the boundary layer? The pressure gradient in the x direction. The pressure gradient, what is it? Is it 0? Is it big? Is it small? What is it? The pressure gradient. I want to know, if I'm inside the boundary layer, I'm right there, and now I'm right there, what is the pressure difference between these 2 points? Inside the boundary layer. You just gave me the right answer outside the boundary layer. The answer was the pressure difference here is 0, nearly 0, right?
Difference.
Now, what's going to happen if I'm inside the boundary layer from this point to that point? What is the difference in the pressure? Somebody have a different opinion?
Because if it's like earlier on, you have higher velocity.
No, it's not going to be high. The pressure difference between these 2 points is going to be roughly the same as the pressure difference between those 2 points. The boundary layer has very little effect on the pressure. Very little.
Or laminar.
Doesn't matter. Laminar or turbulent, doesn't matter. Very little difference on the average pressure. Therefore, when you have a flat plate boundary layer where the flow is going parallel to the plate, the pressure gradient is approximately 0 inside the boundary layer. Okay, let's continue. We're almost done, but a few more minutes and we're done, unless you want to, I can't stay too much longer. But so, if the pressure gradient is 0 in this case, would we expect the boundary layer to separate or not? And form a separation bubble in this case? Would we expect the boundary layer to separate? What do I mean by separate? Creating a big vortex, right? What's the answer? Will it separate or won't it separate in this case?
No.
No. Of course not. Remember, pressure gradients, there's adverse pressure gradients, right? There are also favorable pressure gradients, right? And then there are neutral pressure gradients. Well, this is a neutral pressure gradient. It's going to have very little effect on the boundary layer. Okay, let's do something else. So let's summarize here. What we're really saying here is that boundary layer theory says that whatever the pressure field is in the outer flow is superimposed on the boundary layer. It's impressed upon the boundary layer. The word impressed is used, impressed. I don't know if that makes sense. So you can calculate the pressure gradient inside the boundary layer, according to boundary layer theory, fairly accurately if you know the pressure field outside. Okay, let's go to this case. Here's the same exact flat plate, same one. Except in this case, well, let's talk about this case. This is a case where an airplane is traveling straight in a straight line at 35,000 feet, right? This would be the case of what? Where the airplane is taking off. It's taking off from the airport, right? Okay, there's going to be a boundary layer on the wings. Let's say the wing. Here it is. What kind of pressure difference do you think you're going to get between here and, let's say, over there? Which pressure is going to be bigger? Pressure here or pressure there?
That 2 will be lower. 1 will be bigger. No, sorry. 2 will be bigger.
2 is going to be the higher pressure. Why is that? Why do you say that, Parshva? Why do you say the boundary layer is very, very thin? Why do you say that the pressure here is going to be bigger than the pressure there? Why?
Because of the velocity. Like velocity at 1 is bigger than velocity.
Why don't we draw the streamlines, right?
Yeah.
What do you see going on here? The flow is expanding, correct?
Yes.
It's a potential flow. It's expanding. I can use the Bernoulli equation, right? So the velocity here has got to be slower than it is here because you've got the same mass flow, so the velocity has got to be lower. Therefore, by the Bernoulli equation, the pressure here has got to be higher than it is here. So what case is that? Which one? We already have this case, don't doubt.
Adverse.
Yes, it is adverse. That is correct. That's the reason why takeoff from an airport is very dangerous business, right? Because you have an adverse pressure gradient over the wing. Therefore, it is possible under certain conditions where the angle of attack is large enough. Well, you can get a big separation bubble forming here. That means the boundary layer is literally separating off the wing. And you're getting reverse flow, like we've talked about many times in class, right? And then when that happens, what happens to the drag? Does it go up or down? It goes way up. What happens to the lift? It goes way down. And then what happens to you? You're in deep trouble. Yes. Okay. Now we're talking about the last case. And then we'll go, unless there's some other questions. I think we're talking about some very good things here. So, here's the next case. Here's the wing. Well, this would be the case of, I guess, landing or something. I guess, I don't know, landing perhaps. Okay, here's the plate. Here's a very, very, remember, we just did a very interesting calculation here. The boundary layer at high Reynolds number, which is what we're talking about here, boundary layer thicknesses are very, very small. Right? Very tiny. Okay, here's this very tiny boundary layer. And now now the flow is going this way, right? What do the streamlines look like? Like that, right? What's the difference between the pressure here at P1 and the pressure over here at P2?
P1 is lower.
P1 is lower, correct. So therefore, the pressure gradient is favorable. Why is it favorable? Because if I draw a free body diagram of the boundary layer, this pressure gradient that's generated out here directly affects the boundary layer. Even though the boundary layer is tiny, that's the whole point. The boundary layer is so tiny that it's very susceptible to pressure forces, correct? So let's draw a free body diagram of this boundary layer. Let's put it up here. The pressure here is going to be lower than it is here, right? Pressure here is lower than it is there. Therefore, the pressure gradient is going to tend to accelerate the fluid particle, which is good. Because the other way around is bad, because if we have the other way around, then it would tend to decelerate the particle, possibly reverse its direction, and therefore give you a bad separation bubble. Right. And as you know also, if this boundary layer is turbulent, it's much less susceptible to an adverse pressure change. Right? Much less susceptible. It doesn't mean that it's impossible to separate. It just means it's much less susceptible. And that's the reason why a golf ball that has dimples travels much further than a golf ball that doesn't. Because you've got a turbulent boundary layer there, which is much less susceptible to separation. Okay, I'm all out of. I don't have any more to say. I can't. If you guys have any other questions, please let me know. And,
Are you going to be in your office at all this week in case we have questions?
oh yeah, I'll be here all week, except on Thursday. When
We have our final.
when you have your final run. And you guys know what's going to be on the final, right?
For our
You know